Hi, my name is Kasue, and in this presentation, I will explain how to design a gas quantum well to emit light of a specific color. We will start from the Schrödinger equation, use numerical methods in MATLAB, and determine the well width to achieve the target emission wavelength. In this project, I play the role of the numerical model team in a multidisciplinary engineering company. My task is to solve the Schrödinger equation, estimate confinement energies, and provide the fabrication team with the correct quantum well width to obtain the desired wavelength. So now we're going to have to explain all our mathematical and algebraic processes. We're going to start with our photon energy uh, equation, which is given by this one, which is 1240 divided by lambda in nanometers. Now, this formula relates the photon energy to its wavelength. For example, for a green light, has a value of 550, we can calculate the target energy that the quantum well should emit. Now, the emission energy of the well is approximated as this equation, where we can assume that Eg has an approximated value of 1.424 electron volts, and Eg and is the gas band gap. And E1 ends up being the first electron confinement energy, and EH1 is the first heavy hole confinement energy. Now, given that EH has an approximated value of 0.15 E1, we obtain that E lambda equals an approximated value of Eg, the gas band gap, plus 1.15 E1. And this equation tells us how the band gap and the quantization energies contribute to the total photon energy emitted. Now, then inside the quantum well, the time-independent Schrödinger equation is this one, with the boundary conditions of psi times 0 equals psi times A equals 0. And this describes the standing waves allowed in an electron state in the well. Now, in the finite difference discretization, the second derivative can be approximated by this equation. Thus, the Hamiltonian becomes a tridiagonal matrix with these values 2, minus 1, and minus 1. Numerically solving H psi equals E psi gives us the quantized energy levels. Now, for an infinite well width A, we have these equations, where n can have the value of any number that you desire. So for the ground electron state, we're going to be using this equation. And this provides a simple analytical way of estimating the first energy level. Now, for the emission condition, we have these equations where which we are gonna be substituting it in the analytical formula. And this gives the well width that corresponds to the desired emission wavelength. Now, once A is determined, we compute this equation and the actual wavelength so that this step validates whether the designed well width produces the intended photon energy. So now we're going to have to explain all our mathematical and algebraic processes. This MATLAB program is designed to model a semiconductor quantum well, specifically a gas well with finite potential barriers. The central idea is to stimulate how electrons and holes are confined in the well, and how this confinement modifies the energy levels available to these carriers. Once the quantized levels are known, the program calculates the optical transition energy, which is essentially the photon energy that would be emitted when an electron recombines with a hole. The goal is to match this emission energy to a target value corresponding to a specific wavelength, in this case 550 nanometers, which lies in the green region of the visible spectrum. To achieve this, the program uses numerical methods to build and solve the Schrödinger equation for both electrons and holes, computes the confinement energies, and iteratively adjusts the well width until the calculated emission energy approaches the desired value. This simulation begins by defining the physical parameters of the system. The gas band gap is set to 1.424 electron volts, which represents the minimum energy needed to excite an electron from the valence band into the conduction band in bulk gas. The effective masses of the electron and the heavy hole are then specified. The electron is modeled with an effective mass of 0.067 times the free electron mass, while a heavy hole has a much larger effective mass of 0.456 5 times the free electron mass. These values are crucial since the degree of quantum confinement strongly depends on the carrier masses. A smaller effective mass leads to a larger confinement energy, and while a heavier mass results into a more closely spaced quantized states. Now, next, the code defines the barrier potential, the reduced Planck constant, the electron charge, and the conversion factor between nanometers and meters. It also converts the desired wavelength into a photon energy using the well-known relation E equals to hc divided by lambda. For a wavelength of 550 nanometers, the target photon energy is approximately 2.25 electron volts. Now, the program then initializes the starting well width and sets the numerical tolerance for the iterative process. The well is discretized into 200 grid points, and the spacing between points defines the resolution of the finite differences approximation. This discretization transforms a continuous Schrödinger equation into a matrix equation that can be solved numerically. The Hamiltonian matrices for electrons and holes are then constructed. These are two diagonal matrices where the off-diagonal terms correspond to the kinetic energy operator derived from the finite difference approximation of the second derivative, and the diagonal terms include both kinetic contributions and the potential barriers. Now, to simulate confinement, the potential of the edges of the well is set equal to the barrier energy. Once the Hamiltonians are constructed, the program diagonalizes them using MATLAB's EIGH function. This provides both eigenvalues, which are the allowed energy levels, and the vectors, which are the wave functions associated with those energies. The eigenvalues are converted into electron volts and filtered to keep only the values lying inside the potential well. At each iteration, the lowest electron energy and the lowest hole energy are extracted and combined with the gas bandgap to compute the emission energy given by the sum E emission equals Eg plus Ee plus Eh. If this value differs from the target photon energy by more than the tolerance, the well width is increased by a small step and the entire process is repeated. This iterative loop continues until the maximum number of iterations is reached and until the desired accuracy is achieved. Finally, the program outputs the calculated emission energy, the absolute error compared to the target, the final well width, and the first few eigenvalues for the electron and holes. It also generates a plot for the electron ground state wave functions, showing how the electron is spatially confined within the quantum well. When the code is executed with the given parameters, the target photon energy for green emission is 2.25 electron volts. However, the simulation yields an emission energy of approximately 1.45 electron volts. This leaves an absolute error of about zero point 0.8 electron volts, which is relatively large. The final well width obtained after the iterative procedure is about 15 nanometers. Now, the first three quantized energy levels of the electron are 0.025, 0.101, and 0.227 electron volts. In contrast, the first three quantized hole levels are 0.0038, 0.015, 0.0339. As expected, the spacing between electron levels is significantly larger, reflecting the smaller effective mass of the electron. The hole levels are more closely packed, consistent with the heavier hole mass. The wave function plot of the first electron level further confirms the confinement behavior. The probability density is maximum at the center of the well, around 7.5 nanometers, and goes to the zero at the edges. This is characteristic of the ground state solution in a symmetric quantum well, where the wave function is symmetric and has no nodes inside the well. Physically, these results illustrate the fundamental principle of quantum confinement. Carriers of nanoscale structures cannot take arbitrary energies but instead occupy discrete quantized states. The simulation also shows the sensitivity of the emission energy to the well width and effective masses. In this particular case, the chosen parameters do not allow the emission to reach the desired green photon energy. Instead, the calculated value lies closer to the near infrared region, which is consistent with the typical gas quantum well structures that emit around 870 nanometers. As a really quick conclusion of this simulation is that These demonstrate the application of numerical linear algebra to semiconductor nanostructures. By converting the Schrödinger equation into a matrix eigenvalue problem, it becomes possible to compute quantized energy levels, wave functions, and optical transition energies. Even though the emission energy obtained did not match the green light target, the code successfully captures the essential physics of quantum confinement and highlights the strong link between abstract mathematics, numerical methods, and real engineering applications in optoelectronics.